I am Anil Kumar. Welcome to my series on calculus. Here is the very first lesson on limits. I am going to complete the concept of limits in 3 lessons. First, we'll begin with the basic concepts in lesson number 1, and in lesson number 2, we'll take up the limits of functions which are indeterminate forms and also applications based on them. In the third session, we'll have exam review on limits. So just 3 sessions will complete the whole concept about limits, and then we'll be ready to do derivatives of functions. So in this particular lecture, we will actually focus on the concepts of limits, the very basic definition, how to evaluate limits, limits from the graph, left and right side limits, continuity of a function, types of discontinuities, piecewise functions, and then an introduction to indeterminate forms. In fact, we're actually starting our video with indeterminate form. How? Here you see we have defined limits as limit of sine of x over x, where x approaches 0 is equal to 1. So we are deciding that the limit of this particular function is 1. And how do we figure this out? Well, if we sketch a graph of this particular function, we see that the graph approaches 1 from both sides, that is left side of 0 and right side of 0. You will also notice that in this particular case, sine x equals to 0 for x equals to 0. And you also know that x is equal to 0 for x equals to 0, right? So we have a form which is 0 over 0. And now this form, which is 0 over 0, is referred to as indeterminate form. Is that clear to you? Now, if you have 0 over 0, you cannot actually estimate the value of this function since you know it is indeterminate, right? Now, the idea about limits is actually that limit is you're going close to the point, but you're not there, right? So, even if you go very, very close to the point, you can get an idea of what the value of the function is going to be. And that is the great concept of limit which we are going to look into. And it helps us to solve many difficult questions which were thought at one time unsolvable. Now, let's begin with the concept and see how it goes. So here, let us first define what limit is and how to read this limit of a function as. So here what you see here is that I've written down this particular expression, rather an equation, which you will always find in the calculus book. We have to read it as the limit of f of x, the function, as x approaches a, this value, right, is means equals to L. So that is how we have to read it. Limit of f of x as x approaches a is L. That's what it means, this particular equation. Now, let's try to understand the different terms which we are talking about in this particular definition. A limit is the value that the function approaches as x approaches a specific value. So, a is a specific value, correct? So in this particular case, when we say a specific value, we mean the value a, right? So a specific value. That means when x is approaching a, that's what we mean. Now, what does that mean? X approaching a means that we could be very, very close to a, but not quite there. You understand? So when I say x approaches a, that really means that x get closer and closer to the number a from either side, from both the sides, right? You could approach value of a from both the sides, but you're not at a. Do you understand? So that is the whole idea. So getting back to our example, which we are talking about sine x over x. Now, sine x over x is an indeterminate, right? But when we approach, that is this, when we write that x approaches 0, so when you're approaching from both the sides, then the value approached is 1. And that is what is a real number. And since it is a real number, you're approaching to the same value from both the sides. We say that the limit of sine x over x when x approaches 0 is 1. Perfect. So that is how you're going to read or interpret the limits. Now, let us further dissect this particular definition since we are going to use it many times and in many different ways. So, how do we figure out all other aspects of this definition? So, I'm actually getting from the definition the limit of the function may exist even if the function is not defined at x equals to a. Just as you saw, in sine x over x, the function is not defined at x equals to a. But still, the limit exists and it is equal to 1. Perfect. That's the whole idea. So now, let us again try to understand the same definitions. Written from definition, the limit of the function may exist even if the function is not defined at x equals to a, provided the value of the function approaches L from both the sides. Is that clear to you? Right? So understand these wordings. It says, from definition, the limit of the function may exist even if the function is not defined at x equals to a, provided the value of the function approaches L from both the sides. That is kind of very critical to understand. Perfect, from both the sides, right? So let's highlight this word, rather underline this word, when the function approaches L from both the sides, right? Now, another important thing is, a limit is the value that a function approaches without necessarily being equal to, right? So, because at x it is not defined, so you cannot have a value of the function at x equals to 0. So that is why this particular clause which has been introduced in between is very important to understand. It says without necessarily being equal to as x approaches a specific value. Perfect. Now, the interpretation of this particular clause here is very important. It says without necessarily being equal to. It means it could be equal to also. You get an idea. So read the statement and then try to understand. So let me write down it in a different way. So I'm putting it as a note here, right? So it says without necessarily being equal to. So the two words here is approaching, arbitrarily close, that is one part. So that is must. Now, when we say without necessarily, so the word which is necessarily means that you could be there if you can be. You get an idea, right? So if you have a continuous function, think about a continuous function. Then x can be equal to a. You get an idea. Because for a continuous function, even if you're very, very close to a, and at a, if you can be there, why not be there? That's important thing to understand. So while we take up some examples, you will understand all these concepts. And now, this session is packed with questions. You have to pause the video as we move along, answer the questions before me, and then check with my answer. So I'll go rather a bit slow so that I give you enough time to write down the answers. Well, the concept of limit is not new to you. In the last lesson, do you remember we found the value of e using limit? And that's the reason why I have this particular slide in between. So in lesson 1, what we did was we evaluated the value of e using limits. And there you go. We had a function 1 plus x to the power of 1 over x. Now that is an indeterminate when x approaches 0 because 1 over x is not defined. However, by coming closer and closer to the value of 0 from the left and the right side. So this notation which we used was x approaching 0, that minus indicates approaching from the left side. So this is approaching from the left side. And when we use this notation, x approaches 0 plus, it means you're approaching from the right side, right? So in this case, you're approaching the value 0, right? So you're approaching 0 from both the sides. So this is from the left side. So from left side, as you see, from minus 0.1 to minus 0.0001, which is very close to 1. Similarly, from the right side, when you're approaching from 0.1, 0.01 to 0.0001. And what you approach at is a value which is same. So that is the L value, right? A real number, which is 2.7184, 2.7184, correct to 4 decimal places. Now we used the concept of limits earlier in our session, and that is a recall on that. So I hope now you understand what we are getting into. So now let's move forward with the new function, which is sine x. In calculus, exponential functions e, right, and the trigonometric function sine are very important. And therefore, very early on in our discussion, I've taken both the functions so that you could easily sail through the whole curriculum of calculus without any problems. That's the whole idea. Normally, these functions are introduced much later, but we'll actually begin with them so that we get a big picture and it will be extremely simple for us to move forward. Perfect. So now, what we have analyzed here is that if I write what we have written here right here, we need to evaluate limit, and I'm writing here limit of f of x is equal to L when x approaches a, right? So this is limit of a function exists. What does it mean? It means limit of a function exists at a if and only if value of the function approaches a real number when x approaches arbitrarily close to a from both the sides. Correct? That is what we discovered, right? In the previous example, last lesson. It approaches the same value from both the sides and the value is real. Correct? So that is the definition which we have to keep in mind when we are evaluating limits. Is that clear to you? Perfect. Now, we'll actually begin with the example first and then take up these two questions, right? So don't look at these questions now. Now, in the example, let's figure out algebraically, calculate the value of sine x over x when x approaches 0 from the left side, and also sine x over x when x approaches 0 from the right side. Now here, just as we did earlier in lesson 1 for e, here let's do for the trigonometric function. So beginning with minus 1, getting closer to 0, getting to minus 0.001, when you put the values, what do you get? You get very, very close to 1 itself, 0.999999. And that happens from both the sides. Approaching from the right means really that you start from away from 0 and come closer and closer. 0, right? So approaching. So we started with 1 and then we came closer and closer to 0. 0.001 is very close to 0. That's what we mean when we say approaching to 0 from positive and the negative side, left or the right. Do you understand? Okay, and both ways we approach a value which is 0.999999, and that is 1, and therefore the limit of the function can be calculated as equal to 1. So you could see the limit of this particular function both ways, right? So we just saw this limit using a graph, right? So we could use a graph. Or we could also evaluate as we did this, right? So we could evaluate. So both are the options for you. Now I hope you got the concept. You can take your time now to answer this question. Question number 1. Why limit of 1 over x does not exist when x approaches 0? So we can recall this with the graph. Okay, so let me sketch the graph of this particular function and then you'll get an idea. So that is the graph of 1 over x, correct? What happens when you're approaching 0 from left side and the right side? You approach minus infinity when you're approaching from the left side and plus infinity when you approach from the right side. And these values are not real, right? So they are not real. So it does not exist. Do you understand? When x is approaching 0. That is how you could describe it. Now let me take the other function, which is limit x minus 1 over x squared minus 1. So I like you to pause the video at this stage, graph the function, and then let me know. Well, before graphing, I think you would like to simplify this, right? So when you write this function, you can say, well, we are looking for the limit when x approaches 0. The function could be written as x minus 1 over x plus 1 times x minus 1. And then you could actually cancel these common factors. So we have a whole at x equals to 1. Now once you cancel, at that time you can substitute 0 and what do you get? You get the value 1. Perfect. You get the value 1 because now you have a graph which is 1 over x plus 1. You get an idea, right? So if you sketch this particular graph, 1 over x plus 1 is this particular graph which is shifted 1 unit to the left. And what you really get here is a function which will look something like this. Correct? Now, at x equals to 1, the value is 1. So let's say this is 1 for us. Half rather, right? I'm sorry. So when you substitute 1 here, it'll be half. Sorry. So that is what you get. Because substituting 1 after cancelling, you get this particular value. But remember, at 1, it has a hole. So let me sketch it a little bigger so that we have very less space here though. So what I'll do here is that I will sketch the right. Okay, anyway. So we have a vertical asymptote at x equals to minus 1. The graph on this side is continuous, but on the other side is kind of like this. And in this particular graph, we have a hole at x equals to 1. And there you go, right? So this is this particular hole. And the value is 1 is the x value and half is the y value. So that is the value which you are approaching from both the sides, and therefore the answer is half. But I like you to make a bigger sketch and understand this particular question. Perfect. So I hope that is absolutely clear. Now let's take up the next example. So we have now simpler examples to work with. The difficult part is over since you have understood all the concepts. So now you can sail through these examples. We need to evaluate the limits. 6 examples are there for you. Just pause the video and answer. So the first one is limit of this particular quadratic function. It could be placed in a bracket, that is better way, when x approaches 1. Now this is a continuous function, right? It's a parabola. So it is a continuous function. We could just substitute 1. We can say 1 plus 2 minus 1. The answer is 2. So that becomes the answer, and we can write 2 as our answer. In the second question, limit pi plus 1 when x approaches 1. Well, remember, pi is a constant, right? So pi is a constant, and therefore this limit is equal to pi plus 1. So that is what the answer is. Does make sense to you? Now the question is to find limit of 1 over x when x approaches minus 1. Well, we are not approaching 0. We can say it is equal to minus 1 because when you substitute minus 1 here, you get minus 1. The function is continuous at minus 1 and therefore you can substitute or you can approach so close that you can be there also. So the idea is, if you can be there, why not? Arbitrarily close and then not necessarily. So those keywords are very important to understand. The next question we have already done, but in this case, it is slightly different. We want to find the limit of x minus 1 over x squared plus 1 when x is approaching 0. Well, if I substitute 0 here, what do I get? Well, I get minus 1, and that is the answer. Perfect. The next one here is limit of this particular function 1 over x plus 1 when x approaches minus 1. Well, in this case, as we saw in the graph in our previous page, we found that we have a vertical asymptote at x equals to minus 1, and therefore that is not in the domain. And also, when we sketch this particular function, it's kind of like this. And where is it approaching? It is approaching either positive infinity or negative infinity. So here the answer is does not exist. So this particular limit does not exist. So you have seen that it is not necessary that for every question you will have a value of limit. It has to approach a real value. Infinitely large numbers are not real, and therefore the answer is does not exist. Perfect. The next one is about the absolute function. Now you have to split the absolute function into piecewise function, sketch it, it'll be better for you, and then substitute minus 1 and see what happens and see where the graph should be. Well, x plus 1 means that at minus 1 we have a discontinuity, right? We have a hole at minus 1, correct? So, and the value of x plus 1 is positive on the right side and it is negative on the left side. So it is kind of like this. It is not defined at minus 1. If you approach from both the sides, what do you get? From the left side, you get a value which is minus 1 and plus 1 from the right side. These values do not match and therefore it does not exist. You get an idea. So what is important to understand here is that in many examples, you could directly substitute the value if the function is continuous. Perfect. What else you observe? You observe that does not exist may exist. We may have limits which do not exist, right? So there could be many reasons for that. And two reasons which you saw here is we call them different kinds of discontinuities, right? So let's look into these discontinuities as we move forward. Okay, so one type of discontinuity is infinite. And the other kind here we learned is jump. And before that, we also worked on a hole, right? Do you get the idea? So there are three kinds of discontinuities which you know about, which you learn in functions. And as far as the limits is concerned, it does not exist in the case when the discontinuity is infinite. It does not exist in the case when we have a jump discontinuity, right? But in a hole, it will exist. Since you are approaching the hole from both the sides and you can approach to a real value. That's the whole idea. So if you have a function with just one hole in between, right? Kind of like this. Is that clear to you? In that case, the limit exists. For example, if I have x squared minus 1 over x plus 1, then the hole will be there and the limit exists when we are calculating the limit as x approaches minus 1. In that case, there will be hole, and that is the example which could actually make you understand this particular concept. So in between, I have squeezed in the concept of discontinuity, and we'll move forward into another concept. And this time, we'll see how to read the limit of a function from the graph itself. Now let's see the graph, which is there on the right hand side of this particular table. Based on this graph, we have a couple of questions here. I need you to pause the video, answer these questions. A. Limit of the function when x approaches minus 4. So when I say x approaches minus 4, we are looking at this particular point here, right? So this is minus 4, correct? So what is the limit of the function? Well, the function is continuous and you can write down the value, correct? It seems to be 2, right? So this value here is 2. So the value here is 2. Clear? Now, limit of the function f of x at as x approaches minus 2. So minus 2 from both the sides, it again approaches the value 2. Is that correct? There is a hole. However, from both the sides, you approach the same value, right? So if you approach from the left side or from the right side, you get to the same point. Perfect. So limit is not the value of the function at that point. It is what value do you approach. Perfect. See, at x equals to 0, we definitely have a solid value. It's a continuous function and the value is minus 2. Do you see how simple it is? Limit of the function at x equals to 2. Now at 2, when you look, we are approaching different values. So in this case, we have a jump discontinuity. Perfect, and therefore it does not exist. Now, at 4, what is the limit? Well, at 4, we know the point has a limit of 0. It is on an x-intercept. At 5, we have a value, which is 2. At minus 4, what is the value of the function? When we write like this, f of minus 4. F of minus 4 is the value of the function at minus 4, which is equal to 2. And f of minus 2 is what? At minus 2, it does not exist since we have a hole at minus 2. How about the value of the function at 2 itself? At 2, the value of the function is 4, right? So the solid filled in circle gives you the value of the function, which is 4. And at 4, what is the value? At 4, the value is 0. Do you get the idea? Now we have filled in the form, the table with the limits at different points. And we have also mentioned what is the value of the function. Do you find a connection between the two? Yes, there is. And this is what is important to understand. If limit of the function at x equals to a is equal to f of a, the value of the function is continuous, right? So we can find out the points where the function is continuous. Of course, it is continuous at minus 4. So let me highlight minus 4 to make it absolutely clear. So when we worked out this value and the value of minus 4, we see both the values to be same. And that is what we mean when we say that the value of the function and the limit of the function is exactly same, then the function is continuous. Perfect. You can actually now correlate which are the points which are continuous and you can check for yourself. Does the limit equal the value of the function? If yes, the statement is correct. Perfect. Now let's move on to the next very important concept, and that is one-side limit. We'll actually evaluate limit of a function f of x from either side. Now, till now, we had been saying that evaluate limit from both the sides, but we were directly getting into that point. Perfect. We did start with evaluating from both the sides, but in between, we kind of jumped that particular criteria. Now, again, we're bringing that to your notice. Always remember, when you calculate limit, you have to approach from both the sides, left and the right. And now, pay attention to what is really written. So the very first question A is limit of f of x when x approaches minus 4 from the left side. So we are approaching from the left side. You get an idea? So this particular graph, we are approaching from the left side. And when you approach this particular point, well, you're approaching a value which is minus 1. Clear? So you can write this as equal to minus 1. So that is how you're going to answer. So take a moment to pause this video, write down all your answers, and then check with my solutions. Now, if I am approaching the value at 4 from the right side, so I wrote 4 from the right side there. So we'll go to 4, which is right there, and the value is 0. 0 from the left side. So we are approaching 0 from the left side, we say we are approaching minus infinity, or we can say does not exist. Does make sense to you, right? So the graph actually goes infinitely large on the negative side. 0 from the right side, it goes to positive infinity, we'll say it does not exist. Now, going to positive and negative infinity, it makes sense since, if you want to really sketch the graph, that is a good information. So sometimes we prefer to write positive or negative infinity, but definitely limit does not exist, right? Okay. Now, E is limit of this function when x approaches 2 from the left side. So you're approaching 2 from the left side, you're on this particular path, and you get the value to 0. But when you approach 2 from the right side, you're on that curve and you hit the value 4. Do you understand this part? And definitely, since these two values are different, what do we have here? We have a jump discontinuity. Do you understand? So there is a discontinuity, which is a jump discontinuity. You can clearly see here that there is a jump from one point to the other. That is what we mean by having a jump discontinuity, and the limits do not exist at these points. Clear? Okay, let's move on. We need to find the limit of the function at 2. Now, at 2, we saw that from both the sides it is different. So we will say what? It will say it does not exist, right? And the reason is, now when I say limit when x approaches 2 for f of x, what do? We have to check the limit when x approaches 2 from the left side for the particular function. And that was, if I was approaching 2 from the left side, I was approaching a value 0. And the limit when x approaches 2 from the right side was equal to 4. And we see they're not equal, right? So since the two limits are not equal, so we say 0 is not equal to 4, so the limit does not exist. Does make sense to you? Perfect. So that is kind of very important to understand, right? Now, limit at minus 2, on the other hand, is this particular point. You approach the same value, and this value exists, and it is minus 1. So that exists, as you can see here. Clear? Now, limit of the function at 0 does not exist. We have a vertical asymptote there. And at 5, it does exist. There we have a point, right? And the value is 2. So we can write this as 2. That is how. You have to read the values from the graph. It is not at all difficult. Have a good look at it and try to understand the concept. Perfect. Now let's move on to another very important um, lesson, and that will be on piecewise functions. Normally, this particular chapter on limits is divided into three lessons, which we are covering in the very first one, to give you overall picture, and then we'll get into details with some complicated examination style questions. That is the whole idea. So I'm giving you the gist of it now, and then we are going to explore it in further details in the next lesson, and followed by an exam type review will consolidate your learning and master the concepts. That's the whole idea. Perfect. Now here we have a piecewise function. You can also sketch the graph of a piecewise functions when given. Now the question is, rather let's try to understand the concept. A function is continuous at a if the limit of the function is equal to the value of the limit at a, right? So value and the limit both are equal. That is what we learned, right? So that is to say, for a continuous function, the limit of the function at x equals to a is equal to value of the function. That is what we saw in the previous example, correct? We saw that at these points it is continuous since the value of the function of being approached, no, not at this point, but rather these 2 points, right? So what we saw was it is continuous at these 2 points. Since the value of the function is same, here it is not continuous since the value does not exist, right? So that is continuous. This is not continuous. Let me write down now. So not continuous. And this is continuous. Correct? So these 2 points continuous and these 2 points not continuous. Okay, so let's get back to the example. We'll discuss the continuity of a function which is given to us as a piecewise function. F of x is equal to x when x is less than minus 1. It is equals to minus x squared when x is in between minus 1 and 2, both included, and is equal to 2 when x is greater than 2. We need to understand the continuity of this function. Now, what you see here is that individually, each part or each piece, right? So we could say that individually, each piece is continuous, correct? Now, to make the whole function is they should fit perfectly to make the whole function continuous. Does it make sense? So that is the whole idea. So they should, like at the end points, match up the values, right? So that is what we are trying to say. Now the critical points to check will be these end points. So we need to check which. So you have to check the value of the function at x equals to minus 1, since there is a discontinuity there. At x equals to 2, there is a discontinuity possibility there, right? So there could be. There are the 2 points where the functions are being joined. Now, I'd like you to actually sketch the function with some values, and then what you do is you get this graph. So the graph is provided. Normally, the graph will not be provided. You need to sketch it. So normally, let me write down. Sketch graph. So if you sketch a graph, you'll get something like this. That you could do. Now from the graph itself, you know that the function is continuous here, right? So you can say at this place it is continuous. And here we have a jump discontinuity. Is that clear to you, right? But you don't have to sketch the graph always. I've given you the graph so that you can visualize and understand, yes, that is the case. So what can you do? Well, in this particular case, I would like you to find the value of the function at minus 1. So when you substitute minus 1, in that case, you get actually 2 values. If you are doing here, then you get a value which is minus 1. If I substitute in this, then you get what? Minus 1 square is minus 1, and you again get the same value. Since you get same value at minus 1, the function is continuous. For the second one, we are looking at the value, which is 2, right? So at 2, we have to match up the 2 pieces. Now that means you will put x equals to 2. So when I put x equals to 2 in x square, I get 4 with the negative sign. So here we say f of 2, let me write minus, that is from the left side, is actually minus 4. But f of 2 from the right side is a constant function too, right? They don't match. So we say the limit does not exist. So that is a simpler method. And what I've described now is algebraic method. So I'd like you to actually go through this part again, understand what we did. So what you need to understand here that we have 2 different pieces, and these pieces could be joined. If the joint is at the same point, then the functions are continuous, otherwise not. So you have to check the value of the function at the points, end points of each piece. That makes sense, right? So when we are saying x is less than minus 1, so minus 1 is a critical point to check for both the functions from left and right. So from the left side and from the right side. Does the limit exist? And if it exists, is it equal to the value of the function, right, from one side? So then you could conclude something. On the other end, also, you could just find the value, the function from both the sides. And what we'll find is that if there are different limits, then the function is not continuous, right? So it is not continuous since the limits are different. So the reason is at this point, different limits, right? So we have different limits. I'll write one side limit. So that is enough to prove that the function is discontinuous, but algebraically you can actually get the values, graphically you could show it. So you have all these things to prove. Now based on this, we have a question for you, and that is question number 3. So I'd like you to focus now on question number 3. Find the value of the constant k for f of x to be continuous. So we have given you a piecewise function, right? So we're saying find the value of the constant k for f of x to be continuous for all real numbers, given f of x equals to x plus k, where x is less than 2, and kx squared, where x is greater than equal to 2. You can pause the video, answer this question, and then move further, right? Now this is actually the end of our video. Let us look into the solution so that you understand all the concepts with the help of an example. So here is the solution which I have done for you. So the question is, as you've seen, a piecewise function where we have two different pieces. One piece is x plus k, which is linear, right? So for x less than 2. The other piece is kx squared, quadratic, on the right side of 2. The value at 2 is the value corresponding to the second piece. So this is very important. Where is the value included in the second piece? So there is a possibility of the two pieces to be together at 2. So what should you do? Basically, you find the value of the function at 2 approaching from the left side. Find the value of the function at 2 approaching from the right side. So we did that, right? Now, we have a parameter k. So we have to now figure out what value of k matches. So find k. So then you find the value of k so that it matches. So these are the steps to be followed. So what we did here was we began with saying that the limit from the left side should be equal to the limit from the right side at 2, right? Then evaluate the limit from the left side, evaluate the limit from the right side, correct? Do that. So this is right side. This should be plus. Once you get your answer, which is 2 plus k and 4k, equate them and evaluate the value of k. That is how you have to solve it. So I hope the concept is clear. So the questions could be the other way. That is, find the value of k, the unknown, so that the functions are continuous. Or it could be just check if the function is continuous or not. So that brings us to the end of this first lesson on limits. I hope you have understood the concepts. Perfect. To summarize, we could find limit for any function when x approaches some value. Approaching means not being there, very close. So we are looking for very, very close. Not exactly at x equals to a. Perfect. But another important thing which we noticed is if you can, why not? So if you can, why not is a very important thing to understand. You are approaching something, you're very, very close, but if you can be there, why not? So you could also substitute directly and it works for most of the functions which are continuous. Perfect. For continuous functions, we also learn one important thing, and that is that the limit of the function when you approach a from the left side, if it is equal to limit of the function when you approach a from the right side, then the limit exists. First thing, right? So that is our first thing which we learn. Second thing, if the limit is equal to value of the function, so that is limit when x approaches a for a function is equal to the value of the function, which is f of a, then the function is continuous. Is that clear to you? Now, if you just keep these two things in mind, you are very well off. We did take few examples which are indeterminate forms, but we really didn't go into details. Now, in the next lesson, we are going to see what are the different determinate forms, how to solve the limit related questions easily with those forms. So that will be our next topic. I hope you understood the whole concept, you liked it. Feel free to share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.